one of the two important things which we always worry when we look at molecules is the fact that what happens to molecules when molecules react. Well, there are two important aspects which are associated with this. One is what is called the thermodynamic control, which means that molecules, the products which are more stable are thermodynamically the one which are going to be formed. And so this is what is called the thermodynamic control, which is controlled by the free energy of the reaction. The difference in free energy between the reactant and the product. So the difference of the energy between the reactant and the product, the more is the difference, you would typically expect that that is the reaction which would typically would be favorable. Now, of course, that is not what controls everything, because we would like to have molecules react at within a reasonable amount of time. And what matters in that case is the free energy of activation of the reaction, which is what is called the activation energy. And activation energy, as we know, is the energy difference between the reactant and the transition state. So what we do in most cases is we worry about things like this. So how do you typically make a reaction faster? The idea is, of course, you heat the reaction so that you have molecules which get excited to various other higher vibrational levels, and from those vibrational levels, it is easier for the molecule to climb up the hill and then jump down the transition state. So of course, heating helps, and of course, catalysis. So what happens if you have catalyst, you get alternate pathways which have typically lower activation energies than the pathway which is without catalysis. In this case, of course, you are going to activate the reaction. And the other important strategy which people use is to use something like solvents which can stabilize the transition state of a reaction, so that you are able to make the reaction faster by basically again reducing the effective activation energy between the transition state and the reaction. So these are the typical strategies which people use to make things faster at a reasonable amount of time and to get a reasonable amount of yield. And the difference in the energy between the two is called the activation energy. Now, what happens is the case. Now, the question which people have been worrying, particularly in the context of reactivity, is the following. How does one able to connect the thermodynamics of a reaction and the kinetics of the reaction? In other words, is there something which connects the free energy of the reaction, the energy difference between the reactant and the product, and the free energy of activation of the reaction, which is what is called the delta G double dagger? Now, is there a way to connect the free energy of the reaction with respect to the free energy of activation of the reaction? Now, as it turns out, people have been interested to study this, and one of the first and one of the most classical work has been the work done parallelly by the group of R.P. Bell, and that of Evans and Poliani, which is now known to all of us as what is called the Bell-Evans-Poliani, which is called the Bell-Evans-Poliani principle. And what it says is something very simple. It says that there is a relationship between the activation energy of a reaction and the enthalpy of the reaction. So typically, what Bell, Evans, and Poliani predicted, that endothermic reactions, for which the delta G of the reaction is positive, have higher activation energy, whereas endothermic reactions have lower activation energy. And he, of course, was able to draw a linear extrapolation where he was able to connect the activation energy of a reaction with that of the free energy of the reaction. And over a period of time, there have been several examples. For example, this is one of this very classic example, which is even available in textbooks, which says that when you have dissociation of organic, diazo compounds, you see that for the organic diazo compounds, the activation energies for the reactions which are endothermic are more, whereas reactions which have lower endothermicity, or reactions even which can be exothermic, have lower activation energy. Of course, this is just a kind of a guiding principle, because over a period of time, we know that there are several such examples where there are exceptions. For example, for the case of benzyl radical, this shows an unusual kind of a trip over, and you see that for benzyl radical, the reactant is unusually more stable, even though the activation energy is not that lower. So of course, this arises because benzyl radical in that case has what we know now as aromatic stabilization, delocalization associated with it. Not only in the context of small molecule activation, people have been looking at this for various other examples. For example, there have been evidences. For example, this is the work by Norskov, who has shown that for over metal surfaces, and these are monoatomic metals, monolayers, in which you can see that the activation energies for reactions which are exothermic, right, are lower, whereas activation energies for reactions which are endothermic. For example, the reaction which we are studying here is carbon monoxide dissociation over a metal surface. And you see, for metal surfaces for which the binding energies are negative, I mean the binding energies are kind of dissociation energies are positive, you see the activation energies are also more. So typically one would always look at reactions in which the dissociation energies are negative, for which of course the activation energies are also going to be lower. So this has been a very kind of a very strong guiding principle across the board to design reactions, because the reason why we are interested to connect the activation energies or the free energy of activation with that of the thermodynamics is because it is not a very straightforward quantity to physically imagine the transition state, and we'll come back to it. So it is better to have a kind of a guiding principle from the thermodynamics, even in the context of dynamics. So now, what Bell, Evans, and Poliani said, that the activation energy of a reaction is linearly connected with the reaction enthalpy. Of course, we know now, because this is quite some time back, it was known that there are several limitations. One of the very important limitations which we discussed is that it does not seem to work for reactions or reactants which are unusually stable. For example, the case of benzyl radical, which we consider. And also, from a more theoretical viewpoint, we have seen that this reaction does not work because it assumes, the Bell-Evans-Poliani relationship assumes that as you go from the reactant to the product through the transition state, you have a linear dependence with respect to the reaction coordinate, which we of course know is not right, and we will look at ways to modify this. But as a first guiding principle, it is important to know that indeed there is a connection between the enthalpy of a reaction and the activation energy of the reaction. In other words, you are able to connect the kinetics with that of the thermodynamics. So now, subsequent to the work done by Bell, Evans, and Poliani, there has been a further addition to this work, and which we now know as the Marcus theory. So now, what we have been looking at, what Bell, Evans, and Poliani told, that when you are able to stretch, for example, consider a very simple diatomic molecule. When you are stretching the molecule, the energy increases. But what Bell, Evans, and Poliani said, that this increase in energy as a function depends linearly on the internuclear separation, which of course we know is not right, because from very simple Hooke's law, which you have studied in your high schools, that the energy dependence on the into the length of extension of the molecule, or that for that matter a spring, goes as a quadratic. For example, so what Marcus suggested, that you still have a kind of a picture like you go from the reactant to the product, but then this relationship is not linear, but this relationship is a kind of a parabolic. So the difference between the basic assumption of the work by Bell, Evans, and Poliani and that of Marcus is that Bell, Evans, and Poliani tells this is a linear relationship of the reaction coordinate as it changes from the reactant to the product through the transition state, whereas Marcus theory rightly predicts that it is at least has a kind of a quadratic relationship, at least in the small displacement region. And of course, we know that the energy difference between the reactant and the highest point in this surface, which we will call subsequently as the transition state, is called the activation energy, whereas the energy difference between the product and the reactant is called the free energy of the reaction. And so this is the point which we are trying to make, that the Bell, Evans, and Poliani, even though it gives a relationship, a guiding principle, but at some point of time this is not valid, so we need to go to a little better approximation. So now what Marcus did in his own ways is that Marcus said that you can consider that the reactant and the product are independently two different parabolas, and you assume that the reactant minima and the product minima, the energy difference between the two is the free energy difference between free energy of the reaction, and the energy difference between the reactant and the point when these two parabolas cut, which is here, is what we call the free energy of activation of the reaction, the point where these two curves meet. Of course, and so what his picture is, when you do the reaction, the molecules start climbing, and then fall off from there. So this is the reaction profile which we get. Now, as it turns out, Marcus theory also predicts a different quantity. It also needs to worry about another quantity, which is called the reorganization energy here. And what is this reorganization energy? The reorganization energy is the energy required for converting the reactant into a product geometry without undergoing the chemical reaction. So in other words, you force the reactant to climb all the way up to a point where its coordinate along the x is the same as that of the product. So in other words, you have gone to a product geometry but with a very high energy. So in other words, reorganization energy is a much higher quantity because you are going to force the molecules of the reactant to change their geometry into the product, but they don't undergo a chemical reaction. So there is no chemical change, but there is only the change in the nuclear coordinates. So this is what it's called, the reorganization energy. So these are the three quantities which the Marcus theory has typically depends on. So now let us do a little bit of derivation. It's very simple to do. So what we assume here, we assume that we have two parabolas and both the parabolas are identical. So in other words, we define the first parabola which is nested at 0, 0. I mean, in other words, this is its energy is 0, scaled to 0, and its coordinate, this is only it's a two-dimensional surface. We have energy as well as the displacement along the x-axis, which we assume. And in that case, we assume that the displacement along the x-axis is A for the product, and whereas the energy of the product is lower than the energy of the reactant by an energy which is B, right? So for the reactant, we say that you can represent it as a parabola which is y equal to x square, whereas for the product you are going to again represent it again as a parabola which is only shifted in x and y axis, so which you will write it as y minus b equal to x minus a to the power square. So now of course you can expand this term, and then once you expand this term, you should be able to, but remember, when you expand this you are going to get a formula like this. But remember, at a point when these two curves cut, the point here, these two equations are going to be identical. And once these two equations are going to be identical, then you can of course show that the point where they cut, which we of course now call as the transition state, at that point, these two equations are going to be identical. In that case, you can in fact find out the coordinate of the transition state. Now, what do we find out for the coordination of the coordinate of the transition state, which should be the x dagger here, and then in that case you are going to substitute the terms there, which we of course know is the B is the free energy of the reaction, and whereas A, of course we look at A, and then when you substitute these two inside this equation, and then what you get is a form like this. You are going to substitute this back in this equation, and then what you get is a form like this. What you get is the energy of that term at the energy at the point of the maxima, and you can represent this as this. So now there is a marked difference. There is a marked difference between the form which we have got. Now, what is the form which we have got? We have got a form where the free energy of the reaction, the free energy of activation of the reaction, it has gone as a quadratic term of the reaction energy. And of course, there are other terms, and we will subsequently look at it. So in other words, now we have again connected the kinetics, which is the free energy of the reaction, right? And that again we have connected so this is the kinetics, the free energy of the activation of the reaction, whereas we have also connected the thermodynamics, which is the reaction energy. Now, of course, there is another term which is the A square. Remember, and what is A square? Remember, A square is nothing but the change in the energy required to transform the reactant to product without undergoing the reaction. This is exactly what we have told, and therefore A square is nothing but the reorganization energy. So, and why is it called the reorganization energy? The reason why it is called the reorganization energy is because we are going to reorganize the reactant to the product without undergoing any chemical reaction. So in other words, you are going to require a much higher amount of energy to go to a product geometry, but without undergoing any chemical reaction. So that it goes to the product geometry without going through the transition state, right? So now, as I have told you earlier, that the reaction depends on two things, and the reaction depends on the free energy of activation, depends on the reaction energy and the reorganization energy. Now, substituting for the A, which we have now going to put in, we are going to get a form like this, and this form is what is called the delta G double dagger. Now you can see that the delta G double dagger of the reaction, which is called the free energy of activation, depends on the reaction energy and on this term reorganization energy. Now, as we know from our very phenomenological RNA kind of equation, that once you know the free energy of activation of the reaction, you can right away calculate the reaction rate using this kind of an exponential term. And now once you substitute the free energy of activation, you get an equation for the reaction rate. And what is the equation for the reaction rate which we get? We get a form like this, where again the reaction rate depends on the square of the sum of the activation energy and the reorganization energy. And this is what is called the Marcus equation. Now now the good thing about the Marcus equation is you can break it up into various limits, and then you can see that you get wonderful chemistry coming out of it, which gives you insight into the various kinds of processes which can occur. And we will try to make connections to examples in organic chemistry, inorganic chemistry, physical chemistry, and so on. And we'll look at examples subsequently now. Consider the case, which is the easiest example. Consider the case where you are looking at a thermoneutral reaction, in which the reaction energy is zero, right? Delta G is zero. In that case, of course, you are going to see that the delta G double dagger, the free energy of activation, is nothing but it just depends on the 1/4 of this 1/4 of this term, right? I mean, there should not be a square; it should be lambda by 4. Okay. In any case, in other words, the free energy of activation is only 1/4 of the reorganization energy. In other words, if you want to make reactions faster, you are going to look at thermoneutral reactions. Why? Because thermoneutral reactions have activation energy which are 1/4 of that of the reorganization energy, right? So typically, if you have low reorganization energy, you are going to have low barriers, and of course, low barriers means faster kinetics from the Marcus equation. Now, people have been looking at these reactions for a very huge number of examples. For example, people have been looking at self-exchange reactions, which are thermoneutral. And from that, people have been able to estimate the reorganization energy, and then it becomes right away straightforward to calculate the free energy of activation, because the free energy of activation is nothing but 1/4 of the reorganization energy. In fact, I can show you examples, and people have been, even though the Marcus theory is known from 1950s, late 1950s, but people use this theory for various kinds of reactions. For example, this is a very recent work, in inorganic chemistry by Bill Tolman and Jim Meyer, very, very famous inorganic chemists, who of course write papers on this saying that you have very low reorganization energies for electron transfer processes. Remember, the Marcus theory, even though it is highly successful for redox reactions, outer sphere redox reactions, it is also very useful for explaining phenomena like hydrogen atom transfer reactions or proton coupled electron transfer reactions, where again people use the Marcus theory to explain the kind of the favorable hydrogen transfer from a reactant to the product, and then based on the reorganization energy, the lower reorganization energy, people try to guess that these reactions are going to be faster. This is a very important principle. Now let us look at the function again. Now let us consider the case where, this is the original expression for defining the free energy of activation with respect to the reaction energy. Now consider, we always knew this case, right? This is the very common picture where we know that the reaction is exothermic. So in other words, the product minima is the product parabola. There are two parabolas. The product parabola is lower than the reactant parabola. So of course, in that case, we know that the reorganization energy is of course going to be more than the small activation energy here. So in other words, for most cases, most exothermic reactions, typical examples, would have the reorganization energies which are much more than the free energy of the reaction. And of course, when these two parabolas are sitting exactly at the same point, the cases where they are thermoneutral, shifted of course by A, in that case, the free energy of activation is 1/4 of that of the reorganization energy. So what we can show here is this case here where you can see that when in the case when you have this lambda, the reorganization energy is typically larger than the free energy of activation. You can expand this thing and you can write in this case examples like this. So in other words, you can ignore this term because this is much lower compared to the lambda. In that case, you will of course get a form like this. The free energy of activation is nothing but the sum of the reorganization energy plus 2 times the reaction energy by 4. Now consider the case when you have exothermic reactions. When you have exothermic reaction, the free energy of the reaction is negative. And if the free energy of the energy is negative, then of course this term here, the sum of it is of course going to be lower than the reorganization energy. In that case, for exothermic reaction, the free energy of activation is lower than lambda 4. In other words, for exothermic reactions, what is lambda 4? Lambda 4 is nothing but the free energy of activation of the thermoneutral reaction. So in other words, the point which I'm trying to make sense to you is the fact that when for exothermic reactions, the free energy of the reaction is lower, the free energy of activation is lower than that of for the case of thermoneutral reaction, whereas for endothermic reactions, where delta G is positive, if you use this term, then in this case, of course, this is going to be greater than lambda by 4. In other words, for exothermic reactions, the free energy of activation, the activation energy, is more than that of thermoneutral reactions, whereas for endothermic reactions, the free energy of activation is higher than that of thermoneutral reactions. So in other words, more endoorganic reactions which have positive delta G, have higher barriers. Consider this: reactions which have higher endothermic reactions, in which delta G, you can represent it as delta G or even delta H is positive, you are going to have a large activation energy. Whereas for exothermic reactions or exoorganic reactions, where the energy of the product is lower than that of the reactant, your activation energy is going to be lower. And as it turns out, people have been able to find, and in general, people have found this to be valid across various boards of reactions, whether it is organic reactions, inorganic reactions, physical reactions. For example, I give you an example from material science. For example, people have found that for these kinds of oxide batteries, in which there are these protons or oxide ions hop over the systems, you see the activation energies actually depend if the reaction is exothermic. So the activation energies are much lower if the reactions are exothermic, whereas activation energies are much higher if the reactions are endothermic. So across the board, in general, there is an understanding that exothermic reactions have lower activation energies, whereas endothermic reactions have higher activation energies. As it turns out, that's not enough of Marcus theory. Marcus theory also tells a very specific case. Now consider the case here. When will the activation energy of a reaction be 0? Well, Marcus says the activation energy of a reaction will be 0 when the free energy of the reaction is going to be negative of the reorganization energy. So in the case when lambda is equal to minus G, this term will go back to 0. In other words, you are going to get the free energy of activation to be 0. In this case, of course, you are going to get a diffusion control reaction, because in that case, the rate of the reaction is nothing but the pre-exponential factor. So when do you have the fastest reaction? You have the fastest reaction when the enthalpy of the reaction or the free energy of the reaction is negative of the reorganization energy. Therefore, increasing the exogenicity of the reaction reduces the barrier, and it increases till, the barrier keeps on reducing. If you make the reaction more and more exothermic, the barrier decreases, and you come to a point when the free energy of the reaction become exactly equal to the negative of the reorganization energy, and then you get to a term, you get to a condition where the free energy of activation of the reaction is negative. I mean, is zero. Now, Marcus also did a wonderful prediction. Now, what happens in the case you make the reaction even more endothermic? I mean, even more exothermic. In other case, you have made the reaction, I mean, initially you had things which are thermonuclear, you are going to make it more and more negative. And what happens, you make it down negative. You make it more negative due to the fact that the delta G of the reaction is even lower than the reorganization energy. In this case, you have a very peculiar situation, because in that case, you will see that your reaction energy will become, delta G becomes positive, because in that case, you see this is going to be less than this term, then of course this term again gets back a value. In other words, your free energy, which was decreasing as you are, free energy of activation, which was keeping on decreasing as you were making the reaction more and more exothermic, but it only reduces up to a point. And after that, what happens, if you make it further exothermic, this term again becomes non-zero, and then you start getting an activation energy back. So how do you explain this? So this is what Marcus predicts. So what Marcus tells, you make the reaction. So this is the free energy of the reaction. You make the reaction more and more exothermic. The free energy of the reaction decreases. But then you reach a point when the free energy of activation, the free energy of the reaction becomes negative of that, becomes equal to that of the negative of the reorganization energy. Then if you make it further lower, you get to a position where you again start getting back the activation energy back. In other words, you don't see a linear relationship, but you can go to a point where your free energy of activation no longer will become zero, will become reduced as you make the reaction more and more exothermic, but eventually it will reach a point when you will start to see the things again. Now, so what happens to the rate? Well, the rate happens exactly the same. In other words, you make the reaction more and more exothermic, your reaction rate increases, and it reaches an inflection point here. And after that, if you make the reaction even more exothermic, the reaction rate decreases. Now, this is a wonderful prediction which you get from the very simple derivation which we did for our Marcus theory. And this is what Rudolf Marcus predicted in 1956, and for which he was awarded a Nobel Prize in 1992. Now, this portion of the Marcus thing is known, which is also expected from the Bell-Evans-Polanyi relationship, that which you say that as you make the reaction more and more exothermic, you typically get the reaction, the free energy of the reaction reduced. In other words, you make the reaction faster. But this was something which was not known when Marcus predicted it, because Marcus said, don't make it very, very exothermic, because if you make it very highly exothermic, you will again see that the rate of the reaction decreases. And eventually, there have been a huge amount of data which has experimentally shown that there indeed is this kind of a Marcus-like inflection point where you see that the rate of the reaction increases as you increase the reaction energy. It reaches an inflection point, and then after that, the reaction starts falling. The reaction decreases. In other words, this is the point for which delta G is the exothermicity minus delta G has become equal to the reorganization energy. So in other words, how do you make a reaction most favorable kinetically? By driving the thermodynamics in such a way that the delta G of the reaction becomes equivalent to the reorganization energy. And now there have been thousands of examples now where people have found that this inverted Marcus region, this is called inverted because the reaction rates are not increasing linearly with increase in the reaction energy, but they decrease after this point. This is what is called the inverted Marcus region, and there have been thousands of examples now where people have found such examples to be valid. So now let us recapitulate again. So what we have now discussed is this. The Bell-Evans-Polanyi says that the activation energy is linearly related to the reaction energy. Whereas the Marcus theory says, yes, they are related, but they are related in a kind of a quadratic kind of a relationship. And there is another term which comes in between, which is called the reorganization energy. And it is the trade-off between the reaction energy and the reorganization energy, which decides whether it is going to be a normal Marcus, and normal Marcus is almost equivalent to the Bell-Evans-Poliani, or whether you have this very interesting inflection point where you also see examples where you see kind of an inverted Marcus. So this is what we know from theory. Now remember, we are also chemists. So we now know, of course, how to find out the free energy of activation from the Marcus-like of equation or kind of a Bell-Evans-Poliani. But then being chemist, we are also interested to know what is the structure of the transition state. We would also like to know the chemical nature of the transition state. And of course, we know transition states nobody has seen. And it is not, so people have to guess. And in this context, one of these very important contribution was made by Hammond in 1955. And what he said that, in fact, this is a wonderful title of the paper in Journal of American Chemical Society. It says a correlation of reaction rates. In fact, this article of Hammond remains one of the most cited papers in the history of JACS. JACS is now 142 years old, and this remains one of the top 100 cited papers in the history of JACS. And why is it so much cited? Because it tells you a very simple thing, and it tells you something which is very intuitive. It not only tells you about the energies of the transition state, it also tells you about the structure of the transition state. And what does it tell you? It tells you that if your reaction is highly exothermic, in all likelihood, your transition state would lie closer to the reactant. Whereas if you have a highly endothermic reaction, your transition state would lie close to the product. In other words, you can say that exothermic reactions are reactant-like. You should call them early. Why do you call them early? Because along the reaction surface, you find the transition state quickly. When it comes much earlier than crossing half of the point. Whereas for endothermic reactions, you have the transition state which are late, right? So the point is, you can in fact derive this. And it is very easy to derive it. For example, we have shown this, the simple equation. Now, you remember this was the coordinate of the transition state here, the transition state here, ABC. Now, if you see, if delta G of the reaction, if it is an exothermic, I mean, let us assume it is a thermoneutral reaction, delta G is negative. In that case, you will find that the transition state exactly lies at half of the point between the reactant and transition state. In other words, for degenerate reactions like hydrogen transfer or proton transfer, or which hydrogen jumps from one kind of a Troger-based structure where it goes from one end of the nitrogen to the another nitrogen, your transition state lies exactly in between the two. You don't need to derive it. You can guess it because Hammond's principle gives you a very intuitive way. For exothermic reactions, well, exothermic reactions, the transition state would have a structure which is similar to that of the reactant. In other words, for exothermic reactions, you can guess the transition state to have a structure which is very close or very similar to that of the reactant. Whereas, as a vice versa, for endothermic reaction, we are going to get structures which are going to be product-like. Now, why do we spend so much of time, and why do people would like to invoke the Hammond postulate? Because remember, it is not easy to find the structure of the transition state. Nobody has ever seen the structure of the transition state. You are able to guess, and now the fact that what you have in your hand are the energies of the reactant and the product. So, of course, based on the relative position of the reactant and the product, if you are able to guess the structure of the transition state, this is something very important. And that is one of the reasons why this very simple paper by Hammond has been one of the classics in the field of physical organic chemistry. So, what we have been able to do now for the last some time is that we have been able to connect the thermodynamics and kinetics, and what we know now is that we have this Bell-Evans-Poliani principle, which shows a linear relationship, a Marcus theory, and a Hammond's postulate. Well, as is always true, there are limitations to all of the three models, and one of the very important limitations which has been there is are the cases of the post-transition state dynamics. For example, over a period of time, we now know that reactions, there are several reactions which go from the reactant to the product, but in between the product, what happens after it crosses the transition state, it goes and falls off to two different values. So depending on the on the nature of the valley or the curvature of the valley after the transition state, we are going to get different properties and different structures. These are what are called post-transition state dynamics. So people have been interested to look at it. In fact, we have been also looking at some of these examples. The other limitations of some of these examples which I discussed is the case of non-statistical dynamics. For example, you have again examples. You can have 2+2 Diels-Alder type reactions or 4+2 Diels-Alder reactions. But then what happens? All of them go through the same transition state, and depending on the overall curvature of the transition state and the strength of the motion across the transition state, beyond the transition state, you get a differently favored product. Now, this is something which is not expected from the transition state theory, because the transition state theory assumes that the only thing what depends is the energy difference between the reactant and the transition state. Once it reaches the transition state, it doesn't matter what path it follows, it has to go to the same product. Not necessarily. There are examples now where we know that you can go to a different product. Now, there is another limitation, this limitation we are going to look at it for some time. These are examples of what are called tunneling controlled reactions. So what we have looked at, and let us go back to our model. What we have looked at, we have a reactant and a product, and typically most of the molecules, whether we are looking at Hammond's postulate or Marcus theory or Bell-Evans polyanic principle, all of them have to climb the transition state. However, and of course the energy difference between the two depends on the between the transition state and the reactant is what is called the activation energy. However, as it turns out, there are examples in which the reactant can go and convert directly to the product by actually tunneling across the barrier. Now, why does it tunnel across the barrier? Of course, it tunnels across the barrier because things in chemistry are governed by principles of quantum mechanics, and we know in quantum mechanics that if a wave function is a quantum mechanical quantity, so the description of the particle on the left hand side and the right hand side, if there are not infinite barriers, of course the barriers are not infinite, otherwise there will be no reactions, there would be a finite possibility of the reactant getting converted to the transition state through a pathway which is called quantum mechanical tunneling. And there have been several such examples, and now we have been slowly percolating that idea that you can have tunneling controlled reactions. And for tunneling controlled reactions, we have examples like this. For example, consider this, and this is a work by Peter Steiner, one of the very celebrated work, in which he has found that even though an OH bond, this is a carbene which can reorganize, this OH bond can reorganize, this carbene can reorganize by either conversion of this OH bond there or a CH bond. OH bond is typically stronger than a CH bond, so you would not have expected an OH bond to migrate, but what happens, the OH bond has a smaller width. And in quantum mechanics, reactions, the probability of transition between two states depends on the width of the barrier. So if the width of the barrier is low, even though the activation energy is higher, you can still have tunneling. As a result, you can have an exclusive product of the tunneling control product. And there are other examples as well. So typically the important message is a small width of the barrier assists quantum mechanical tunneling. So how do you know? Experimentally, how will one know that there is quantum mechanical tunneling occurring in this reaction? So typically we would see that due to tunneling, the particles are not only going over the barrier, they're also going through the barrier. So as a result, the overall reaction rate will increase. And what you will see that for the RNAs plot, the logarithm of the rate versus with respect to the inverse of the temperature, which of course we know from RNAs plot is going to be linear relationship. However, when you have quantum mechanical tunneling, as you reduce the temperature, we are going to see the reaction rates to be significantly higher than that what you expect from Martinez principle. As a result, you will have a temperature independence of the chemical reaction, and as a result, you will see a curvature. Of course, the other important point by which you can recognize or find out mechanistic pathway, whether it is going through the barrier or over the barrier, is to look at the kinetic isotope effect. And what do you do in a kinetic isotope effect? You have protons, you have CH, and then you try to typically replace them by CDs. Now we know if hydrogen and a deuterium, they are chemically equivalent, other than the fact that the deuterium is twice as heavier as a hydrogen, and also as a result, the 0-point energy difference between a CD bond and a CH bond depends on, of course, of many things, at least at the 0th level, at the kind of inverse of the square root of 2, right, in the masses. The other thing is, of course, that deuterium is heavier than proton. So as a result, the probability of tunneling, quantum mechanical tunneling of a heavier particle is lower. So of course, when you have isotope effect, when you replace a hydrogen by deuterium, you are going to see a much larger jump in the reaction rate than what you expect. So typically, when you have large isotope effect, you would typically invoke quantum mechanical tunneling, which is occurring in the reaction. And there have been several such examples. For example, people have, for example, this from our group. These are kind of carbenes, and then carbenes can dimerize, and it can also undergo kind of dimerization reactions, in which you can see that the protons move, and you can have also intermolecular dimerization reactions as well. And interestingly, for these reactions, the barriers, for example, the barriers depend. For example, the case of 3A to 3B, this barrier of the reaction is very, very low. It's about 2 kilofarad per mole. Now, if the reaction barrier is very low, you would expect that the particle, it would be very easier for the particle to tunnel across the barrier or jump above the barrier. So as a result, you will have a situation where the particle is not at the ground state, where the particle is vibrationally excited higher, at a higher level. So in that case, you are going to get a very weird example of what is called quantum mechanical deflection, where the particle can also, typically the particle can tunnel, the particle can also go classically from this state to this state. However, when the barrier is very low, the particles are here. In this case, even though it does not face a physical barrier, that is because of the nature of quantum mechanics, which is called quantum mechanical reflection, only half of the particles will be percolating down there, that side. So as a result, you will see an example where even though you include quantum mechanical tunneling, you will see that the reaction rates are actually slower than what you expect classically. And this is a kind of a weird example, which is interesting. Right. The other important thing which also arises due to quantum mechanical tunneling is this example. Now consider this case. How long a carbon-carbon bond can be? For example, we know one of the classic example, but a carbon-carbon single bond length is about 1.454 angstrom. Can we make it longer? Well, you can make it longer by putting very big steric groups. For example, if you increase steric congestion, for example, people have put adamantine derivatives, you see that this bond length can be stretched down to 1.7 angstroms. Can you make it longer? Well, people have tried to make it longer by making this kind of compounds which are called carboranes, and this kind of carboranes are examples where you can see that for these cases the nitrogen lone pair interacts with the sigma star, the antibonding sigma orbital of the CC bond. As a result, the electron gets transferred from this to this, and as a result, this bond gets really stretched. You can make this bond even longer than 2 angstrom. In fact, this phenomena, transfer of electrons from the lone pair to a sigma star orbital, is what is called negative hyperconjugation. And we have been interested in this molecule. For example, last year there was a wonderful report where people have made a molecule like this, which has a bond length of about a carbon-carbon bond length of about 2 angstroms. Interestingly, if you look at the crystal structure of the system, you will find that this molecule here has a very planarized nitrogen. Now, if you have a very planarized nitrogen, this represents your transition state, because for amine inversion, nitrogen is pyramidalized. For amine inversion, the amine gets converted from this end to that end. As a result, for amine inversion, you will see, so this is a structure, this is a ground state for which the nitrogen has a planar structure. So of course, the reason why this has a planar structure is because it has a very small barrier, and as a result, the reaction is happening very fast. And of course, it has huge contribution from the tunneling of the hydrogen atoms across the nitrogen. And because of this rapid tunneling across the path, you will see when you take an average of the picture, when you take an average crystallographic picture, you will see that this nitrogen is planar nitrogen. So in other words, you have been able to stabilize in some sense a transition state like structure. It is not a transition state like structure, it is a ground state structure, but the fact that it is flipping so fast that you have been able to kind of freeze this structure in a transition state like geometry. So this is something which we have been looking at, just looked at some time back. So the idea is transition states are very interesting because transition states govern dynamics, transition state governs kinetics, and it's also very interesting to see the structure of the transition state. Long back in 1955, Hammond asked us, gave us a very qualitative picture. That is one of the reasons it is one of the most cited paper of JACS to guess the structure of transition state. Now in 2020, we are also able to see the transition state in a different way. We are able to see the crystal structure of a transition state. We can see a planar-like transition state structure. And this work was done by my students Nilangshu and a summer student who visited us from University of Hyderabad, Ahsan, for a few months. And then this is the work which we had done. In other words, we have been able to look at a transition state, a planar amine, which almost resembles the transition state-like structure. So with this, I thank you very much for your patience. And of course, we thank by saying namaste, and looks like everybody in the world does namaste to everybody else. So I also say namaste to all of my friends who have spent all the time and wishing a very wonderful evening today. Thank you very much.